explain the physics that underlies the Hamiltonian structure. That's the Poisson matrix for Ehringen's theorem. Ehringen's theory. I'm going to try to explain some of that. I'm going to concentrate on the inner variables, which are these here in that part of the Poisson matrix. So the equations are gotten by just doing matrix multiplication of these operators on these variational derivatives. Okay. I'm going to concentrate on the inner variables. I'm going to discuss complex fluid order parameters that are associated with broken symmetries, in particular SE3 symmetries. There's some connection with an analogy with Yang-Mills theory. And I'm going to talk about to determine some conditions about the nonlinear wave equations for complex fluid or complex media. If the fluid is not moving, that admits soliton solutions. And the way of finding the soliton solutions is to get a lax pair for the problem. Okay, so it turns out that this is not the talk I wanted to give you, because I wanted to introduce a bunch of things first. So let me try to introduce those. Okay. So I want to talk about order parameters. Okay, and I want order parameters, I want to think about order parameters as elements of, I'm going to talk about, first of all, I'm going to talk about, elements of a coset space of, so we have Lie group G and the subgroup H. Okay, and so the coset space, so let's call it, so coset space C is a space of for G in big G and H in the subgroup called, in physics it's called the little group, right? Let's go back to Wigner in the 30s. So this is a space where G in the group acting on H in the subgroup is the orbit of points in the subgroup under the action of the group. Okay, so I claim that, well, I don't claim. Louis Michel characterized the various types of complex fluids according to the broken symmetries of the special Euclidean group, broken by the symmetries that remain. The subgroup is the symmetries that remain after the big group is broken. Okay, so the point about this is that G acts on its cosets and takes the coset space into the coset space. Okay, and so we can write we can lift the evolution of the order parameters into an evolution on the group. And it can be space-time evolution. So if we take, what we'll say is that C in a coset space, depending on space and time, is equal to some element of our group, depending on space and time, acting on the initial condition for C. Thanks for that nod. Okay. Okay. And what I actually, yeah, okay. So so this is going to give us an opportunity to lift to dynamics of G. Okay, because we can take time and space derivatives of this element of the coset space. This one's fixed. This one depends on time. So if we can get an equation that lives on the group, then we can come back and get the evolution of the elements of the coset space by acting with that. So we're going to pack all our physics into this.
T is time, what is S?
What?
T is time, what is S?
S is space.
Okay.
Okay, space and time. Okay, so let's think about just space as S is a one-dimensional object. Okay, so you have one-dimensional space and time. Okay, so I want to define derivatives with respect to space and time that are invariant, let's see, under, let's see, I'm going to write it as subscript for derivative. And they're invariant under left actions of the group on itself. So if we replace, so this guy is invariant under G goes to KG, right? And then G inverse goes to G inverse K inverse, and GT goes to K G. We multiply them together, okay, and then this takes G inverse GT into G inverse GT. So I'm making this point because so I want to define variables which are tangent, right, to the derivatives of G, but then pull back to the identity of the group by G inverse. And the tangent space at the identity of the group is the Lie algebra. And so we're going to define Hamilton's principle in terms of elements of the Lie algebra, G inverse GT and G inverse GS. And we're building in invariance under, left invariance under G for for this Lie algebra. Okay, so we're going to, our Lagrangian is going to take two elements of the Lie algebra into the reals. But before we construct a Lagrangian, we want to make sure these two guys are consistent. So if we take the time derivative of this guy, we'll get a GTS. And if we take space derivative of this guy, we'll get a GST. Okay, and this guy is equal to add omega with the plus sign, right? Okay, so this is our compatibility condition. Between these, the big omega and little omega. Okay, but this is also an evolution equation for big omega, and it's going to appear in the Poisson bracket. Okay, so the first part, one part of the Poisson bracket is just compatibility. So the other part is going to come from, oops, that doesn't go up. Does it?
Will you be giving us a simple example at some point?
What?
With this, a simple example, this structure, I mean, how one can look at a simple physical problem so that one can
Yep.
add loop to
Yep,
something like
yep. I'm give you a list. in a
that. No,
little
just
while.
one example would be helpful.
Yeah, one example too.
And this compatibility, I mean, what is the, I missed the point, I mean, what does it make compatible? I mean,
Oh, compatible. Compatibility is that GST equals GTS. So I mean equality of cross derivatives. Okay, so let's do that. Omega sub t, this one, is minus G inverse GT inverse S, which is equal to little omega times big omega, and little omega sub s is minus G inverse ds, G inverse dt, and that one is minus, oh, this guy here is minus big omega times little omega, and omega sub t minus omega sub s is equal to minus in this one, so it's omega like that, okay, which is, I wanted to define this object. This is the Lie bracket, okay, under the algebra, and I want to define this notation. It's minus like that, so the sign is minus. Okay, so that's what I mean by compatibility. I'll just erase it. So far we've put absolutely zero physics into this. This is just coming from definitions of these variables. So let's put some physics in. The physics will come from Hamilton's principle. Which is variation of s is 0, and s is the integral of the Lagrangian depending on omega, big omega, dt, and this is, and I'm gonna write it as the Lagrangian density, so I'll write it as ds dt, so that I can take integrations by parts easily. So this guy is the integral of dl d omega plus dl big omega ds dt. So what we need to know is if this is omega, then what is delta omega? Okay, but we've just done this calculation. Okay, by the same kind of calculation, we can do, say, let's call this thing omega prime. It's G inverse GT prime, which is minus G G inverse prime gt plus G inverse G prime. Okay. So this guy, okay, so if we calculate, this is delta omega. So if we define another quantity called C, say, as G inverse delta G, and we take the time derivative of that one, we get an expression for delta omega, which is the integral dl d omega times c sub t plus add omega c dot. Okay, this guy's delta omega. Okay, if we add, so now we want to take delta big omega, and we'll do the same calculation except there'll be a c sub s there. So which is delta L, delta big omega, c sub s plus add big omega c ds dt. Okay, so is this step clear? Right? It's the same calculation as this one, except we're taking variational derivative instead of the other space-time derivative. Okay, yes? So at this moment, I want to integrate by parts. So it'll put a partial time derivative on dl d little omega. It'll put a partial space derivative on dl d big omega. And it'll take this guy over to the other side. If I want to get everything paired with c, so I need to define something. I'm going to keep this one. So I want to define something. This guy is a pairing that takes, well, omega's in the Lie algebra. dl d omega is actually in the dual of the Lie algebra, and it's the vector dual. So this pairing takes something in the dual of the Lie algebra, something in the algebra, into the reals. Okay, and we can use it to define another quantity. Let's see. So I'm going to say mu, which can be one of these variational derivatives, will be in the dual of the Lie algebra, and add omega c. Right? So we want to get this add to the other side to get c by itself. So we can use Hamilton's principle. Okay? So we define a new symbol for that as add star omega mu paired with c. Okay, this is add star. So we can do both of these operations now. We can integrate by parts, and we can bring the add over to add star, and we can collect all the things that pair with c, and we have partial with respect to t with a minus sign, dl d omega, plus and star omega, dl d omega, minus the spatial derivative, dl d big omega, plus add star big omega, dl d big omega, all paired with c dt. And this is 0. C is arbitrary. So we've just done Hamilton's principle on a Lie algebra. Okay? The equation we get is d by dt of dl d omega is minus add star omega dl d omega minus d by ds and dl big omega plus star dl big omega equals 0. Okay, so this is the Euler-Poincare equation. Okay, for this Lagrangian, and it implies a map of two parameters s and t, and c r cross r into the group G. Okay, it implies it because after we have constructed the solution for the Euler-Poincare equation, we have a relationship between dl d omega, little omega, and big omega, and knowing the solution we can reconstruct from the tangent space we can reconstruct the map on the group. Okay, so this is what Tudor said. Okay, so let me show you in these terms some of the results from this theory.
So, is it supposed to? Am I supposed to say that the left-hand side and the right-hand side are both equal to 0, or does the left-hand side?
Because this one was started out being set to 0.
Yeah.
It's equal to some expression paired with an arbitrary element of the Lie algebra. Okay,
Yeah.
so if it's paired with an arbitrary
Yeah,
element,
so-
then
yeah.
the coefficient must be 0.
Yeah. Okay, but I guess you have. I think there's an extra 0 which I don't see.
Oh, no,
Equal to
I
0.
see. No, I carried that one to the other side. And did I do everything? I did. Thanks a lot. Let me fix these signs. I was miswriting as I went. I changed all the signs, and then I took, or let me just take this one to the other side, and then this one is left as a plus, that one's a minus, and that one's a plus. Thank you. It's locked. I have to get it unlocked. Will you set me up again?
Yet.
See how much time I've used. Okay. Oh yeah. So here's an N star. Okay, and that goes here. Oh, and here's another N star. Right, that's this one here. Oh, here's a D by DS. Okay, that's this one. And here's an add. It's this one. Here's a D by DS. Whoops. Here's the add. It's that one. D by dt, D by dt, D by ds is this one. So this is the part of the Poisson matrix. So we have to now do, from here, we have to do a Legendre transformation. And that's not difficult. So this guy, the one we just derived, is this part of the Poisson matrix. And if we couple it back to the fluid, so that motion on of the order parameters can cause motion of the fluid, and motion of the fluid can pull the order parameters around in the flow, then it's a complex fluid, and you have to add these other parts of the Poisson matrix and get variables for the outer, getting equations for the outer variables, whereas if we don't have any flow, we can ignore the outer part of the Poisson matrix and just look at the inner part. And so that's what Tudor was talking about. In Aragon's theory, there is an outer set of variables, these are fluid variables, and an inner set of variables for the order parameters. Okay, now this is actually, these are not order parameters, right? This sigma and so forth. These are Lie algebra and dual Lie algebra quantities. Okay, and you've got to get the map to G and then operate on your order parameter to find out how the motion goes with the order parameter. Okay, so what else did Tudor say?
So, sorry, another question. Is there any constraints on your little L? So, what?
This cell here?
Yeah.
Yeah, this is where all the physics is going to go. Okay, so for each of these complex fluids, we will always have some input in the physics, okay, about what the dynamics is. It'll always have this shape, though. That's why I call this thing, let's see, the shape. It'll always have the same, shape, but you can have different Lagrangians or Hamiltonians, and you can have different order parameter groups. You can define order parameters as different coset spaces of the various groups, but the equations will always have the same point. And why is that? These equations are equivalent to the Euler-Lagrange equations on the group. Okay, we've just used the invariance of the Lagrangian, this was left invariance under the group, to write our original Lagrangian in terms of invariant quantities. That's always a good idea. Whenever you have a variational principle which has an invariance, write the variational principle in terms of the invariant quantities, then take the variations. And you get, and then this equation then loses no information because you can reconstruct G from that solution. Okay, another thing which is kind of fun about this, what am I doing? Yeah, is here, look at this term here. This says gamma sub t is equal to this operator on dHd sigma, right? This operator is the covariant spatial derivative. Okay, so this is bringing in geometry and covariant derivatives that live on Lie algebras. So this is part of the answer to my question here. What does the dynamics of complex fluids have to say about geometric mechanics? Well, it's so inspiring, right? You look at these equations and you say, oh, there's something about this. Really is intriguing, and then eventually you trick onto the structure that there's so much about the problem which is geometric. This guy here is this one in this notation. He's just a compatibility condition, but he's bringing in all this geometry. He's bringing in covariant derivatives defined in Lie algebras. This guy here, this guy times that one plus this one times that one, that's the Euler-Poincare equation. So now that we've done this and we understand this much, if we concentrate just on these inner variables, then we have more to say. Okay, any questions? Yes?
So when you couple this with a flow, fluid
Yeah.
flow, the time derivative is Lagrangian time derivative of Eulerian.
No, it's more than that. Because if these things were just scalars, then it would just be the ordinary Lagrangian d by dt.
Rotation.
But these things, this one here is a one form. This one here is a one form density. So you have to take into account, so for any tensor, it's still d by dt of that tensor, provided you keep holding onto the base of the tensor also, and so that you take the derivatives of the base of the tensor as well as the coefficient.
Space derivative is the space derivative.
I can't hear you much.
Yeah, the space derivative is
The space derivative
for
here?
the parameterization of initial data, or yeah, what is the derivative with respect to S? In a
Grad.
flow, when you couple with a flow,
Grad.
the grad.
Yeah, spatial grad. Yeah, it's this one.
So
Grad.
it's the Eulerian grad.
Grad into,
It's Eulerian. I mean, it's just the gradient.
yeah, just a gradient. Right? But that's the bare gradient right there. And this is the thing that makes it the covariant derivative. Okay, this guy, so that tells us more. It tells us that gamma is a connection form that defines a covariant derivative, and it lives on a Lie algebra. So it's a Lie algebra valued connection form. And what does that remind you of? What does it remind you of? This is Yang-Mills, right? That's exactly the setup for Yang-Mills. Okay, so there's going to be an analogy to Yang-Mills of the structure. The structure itself exists on its own. It doesn't have to be a Yang-Mills theory. It just has some components which are like Yang-Mills. It's actually, my way of thinking, it's more interesting than Yang-Mills.
Well, Yang-Mills has gauge invariance, and this one has not.
Gauge, no, this one doesn't have U1. It has G. It has a non-abelian gauge invariance. Right? So Yang-Mills, say, has an SU3 gauge invariance. This one here has the gauge invariance of the action of the broken symmetry.
No, but it doesn't have local gauge invariance.
It sure does.
No,
Yeah, it does.
because the
That's
gradients,
that guy right
the
there.
gradients of
That's the guy right there. Okay, that's the local part of the gauge invariance. Exactly. Okay. So, I told you that all of the complex fluids can be written as the order parameters can all be written as coset spaces of the special Euclidean group with it broken to a subgroup, and when it's broken to this subgroup here of d infinity h symmetric product on R3, well, that's equivalent to RP2, and then you're looking at nematic liquid crystals. Okay, and now in this case here, SE3 is a space, is SO3 cross R3. This guy is a space, is the D infinity cross R3, And the R3 is transparent, and then you now see it as SE3 mod SO2 with reflections. Okay, but I'm gonna do the whole reduction. This is, let's see, here we are. There'll be some guys from the Lie algebra. These are the guys we just looked at, SO3, and there'll be other guys that correspond to the spatial, breaking the spatial translations, and these guys will be in R3, and the order parameter in this case is going to be in RP2.
So, sorry, can you construct things where you can break time reversal symmetry? Things which, so could you have, so you could have just defined an L which breaks time reversal symmetry somehow?
No, I still always have L defined in terms of the Lie algebra quantities of the unbroken symmetry. Okay? The things that this guy acts on are things in a coset space, for example, in this guy rho, which is, it's doing the same thing as I said earlier. It says that let's call it, I don't want to call it a director. Let me just call it the order parameter at some time is equal to a group element as a function of space and time acting on its initial condition. That's what this says. Okay, and this is going to have particularly simple result, because then d by dt of rho is just rho cross dh d pi, and dh d pi is omega, so that's just precession of rho in a frame, which is moving under SE3. So SE3, motions of SE3 are rotations and translations, so they can be any space curve you like. And the rotational part of that is what propagates the time and space dynamics of the coset variable. Okay, if we were really talking about liquid crystals with no flow, well, that's actually one of the Leslie-Erickson equations. This one here. Okay, so I'm just telling you that if we go all the way to breaking SE3 with symmetries that correspond to, breaking SE3 to subgroups corresponding to the symmetry of the complex fluid, then we have a space, a coset space, on which the original unbroken symmetry acts, and we write down our action and we lift it to the group, and then we compute our compatibility condition and our Hamilton's principle for the Euler-Poincare equation, and that's it. That will describe the dynamics. And if you do that, this is what you get for breaking SE3 with respect to SO2 with reflections. The reason why there's so many equations here is that SE3 is a direct product of rotations and translations. So there's going to be an angular momentum and a linear momentum. Okay, and there's going to be an angular velocity and a linear velocity. So that all has to go into the equation. And then there's reconstructing our element of the cosine space. Okay, so this is just a, what is this? It's just an unpack this matrix. It's just let you know that if you operate with this matrix along for the top row X on the column of variational derivatives, then you get the d by dt of pi. The next one for mu is the second row, another variational. You get this guy. Gamma is just these two, and omega is just that one, and rho is this one. Okay, so this is a way of seeing the shape of the Poisson bracket, because the entries in this matrix are the entries for the Poisson brackets. Like pi with pi is pi cross. Pi 1 with pi 2 is pi 3, and cyclic. Okay, so I want to parse this out. I'm going to just tell you that this much here is the rigid body in the upper left corner. The top two in the upper left corner, that's SE3, that's the heavy top. Okay, and then when you add spatial dependence, then you get all these other terms. So let me say that in words. If you look at what is the Poisson bracket for the heavy top, and you write it in this form, there's the heavy top equations. Then you see that this upper left corner is just the Poisson bracket for the heavy top, and we know that the dynamics of this system is going to be interesting because heavy tops can do a lot of things. Okay, if we add the S dependence, then we get these other two rows, and finally, if you add the action on the coset space, you get the last one. Okay, so here's what I was saying at the beginning. Louis Michel, in 1980, classified order parameters, defined them as coset spaces of SO3 or SE3 for broken symmetries of rotations and translations, or both. Okay, so a good number of the things we know and love are classified by G mod H, where the G is the broken symmetry, SE3, and H is the symmetry that remains. Okay, so in each case we calculate the coset space. We have this equation and this one for the evolution of the lifted to the group of the dynamics on a coset space. And it always has the same shape as before. Always has this shape. And all the physics goes in right there in the Lagrangian. Okay, so if you choose a theory like Leslie Ayrton or Aragon, and you ask where does the physics go and how do we extract it? Well, this is the shape it has, and then the Lagrangian determines the actual details of the equations. Okay, so that's what I'm saying. The action of SE3 on its coset spaces, SE3 mod H, determines the contribution of the order parameter to the overall dynamics. So we should talk about this. If we only just talk about the simplest ones, we can still talk about this. And this is what Tudor was saying. This is this Aragon theory. Okay. So, it's probable that studying this action on the other coset spaces seems to be the right way of modeling the dynamics of the other complex fluids. And then once the inner dynamics has been constructed for the complex fluids that are on Michel's list, or on other ones, the one, your favorite one, then the outer dynamics can be formulated just by extending that bracket to the one Tudor showed. And also, once we're in this framework, then we can do more than just add this diffusion. We can add a type of dissipation that respects the geometry of the variables that have the Hamiltonian or the Poincare variables. Now, think about that. So how would dissipation look if you're going to keep track of the transformation properties of the equation? So the whole equation transformed properly, and the dissipation terms and the Hamiltonian terms transform the same. They don't transform differently. Okay. So, a couple of ways of doing this is with Rayleigh functions. Another way, which is really nice, is that here we have these single brackets. With dissipation, that's part of the story. With dissipation, you can get energy to decrease by raising your bracket from a single bracket to a double bracket. And then it transforms properly. Okay. And here's a remark about this analogy with the Yang-Mills theory. This is that Tudor's matrix again. Gamma is a one form on the domain, which takes values in SE3. Okay, so this would be Lin would be an SE3 gauge theory. Okay, and sigma is a gauge charge. Okay, it takes values. Sigma, what is sigma? Sigma is what we call big gamma. Let's see. Well, I forgot the alphabet connection here. But the part that comes here in the third slot, okay, in the inner variables, and it goes right there, is the analog for Yang-Mills theory of the charge. Okay, and the minimal coupling for such a Yang-Mills theory, it would be charge times magnetic vector potential, charge times vector potential, and here it's the pairing of sigma with gamma. Okay, and that'll give you minimal coupling to the fluid. Okay, so one of the features about that is that it might be useful in discussing what we mean by charges and defects of various kinds in complex fluids. Okay, so those are the sorts of things that geometric mechanics inspires in mathematics. And it takes mathematics to a place that wouldn't have gone just by itself. And it opens, as well, it makes a unifying viewpoint of the complex fluid dynamics in the absence of dissipation and forcing. Gives the Hamiltonian part. It tells us how the dissipation part has to transform. And then the really interesting feature is that damp-driven nonlinear Hamiltonian systems are always interesting. And they're interesting when the forces and balance and dissipation are comparable to the nonlinearity. That's when they get really interesting. So one of the features that we can study about this part of the Poisson matrix is that these guys, for sigma and gamma, are wave equations. Okay, so these, right, because here's a d by dt, here's a d by d spatial derivative. There are two coupled ones. It's a hyperbolic system. It produces waves, and these are waves in the order parameter that in a medium, in a complex medium, which is not moving. Okay, these are the equations for the waves. So I won't tell you much more, but thanks for listening.
This general relativity you can also put into this framework. Yes?
What?
General relativity can be also put in this framework.
Actually, it's true. In fact, general relativity coupled to a fluid. The general relativistic adiabatic fluid can be put into this framework, exactly this framework. In a particular what's it called, method called the ADM approach for Arnold, Desner, and Misner. Yeah, so ADM general relativity has this form.
But it will always include torsion, right? Because
Yeah, it includes torsion, yeah. Right, it's pretty general. And it's another thing about general relativity is that one of the subtlest, most interesting features that's the most difficult to impose is a thing called constraints. Okay, so there's a constraint on the initial conditions for the equations of general relativity. And it's those constraints that completely destroy the approach of quantum mechanics to general relativity. But in this framework here, the constraints turn out to be like Gauss's law in electromagnetism. If it holds initially, it always holds. So they're just dynamic. They're dynamical constraints. They're not like non-holonomic constraints or something. Any other questions? Yes.
Yeah, I remember at the beginning you promised that you would produce a Lax pair for your equations.
You want to see it?
Yes.
Anything else before that?
Yeah, another question. When you showed the table by Michel, I mean, so you have to decide a certain phase you want to look at. But what if you want to look at the transition between phases? Like between isotropic and nematic and elliptics?
Well, that's a fabulous problem. I haven't thought about it at all. Have any ideas, Jessary? Yeah, it's just not something. Yeah, but it can happen. It can happen, and it will be some kind of spontaneously broken one kind of symmetry, and and then creation of another kind of symmetry. Phase transition. It's probably like the next thing beyond the phase transition to liquid crystal, right? Because there you can go from a isotopic fluid to a fluid that loses isotropy, and then maybe it can have more second order phase transitions. I love that question. Okay, so Antonio, right?
No. Spiros.
Okay, so I'm calling these equations for the inner part of the Aragon theory, the G-strand system. Okay, here's our guy. d by dt of the momentum guy has an add star. d by dt of the velocity guy has an add. Okay, and this system, this guy is on the dual of the Lie algebra, this guy is on the algebra, and it's a set of in Euler-Poincare equations and in compatibility conditions. Okay, and it produces, as you see, there's linear derivatives in space and time and quadratic nonlinearities. Okay, so here's the theorem, is that a sufficient condition for the Euler-Poincare equation, which is written in terms of the add stars, to be expressible in terms only of adds, okay, is if add star is equal to minus add. And this works for SO3, and it works for any semi-simple group, and it may work for many more groups like SE3, provided you do some other interventions. Okay, so the corollary is that, so the corollary is that we can write our G-strand system only in terms of adds, in which case we immediately can write it in terms of what's called a zero curvature relation. Oh my goodness. Okay, one more. Yeah, okay. So this is the Lax pair. Okay, and these are this is the L operator and the M operator, and it turns out that the conditions for this to hold give relationships among gamma and omega, and big gamma and big omega, and they're constitutive relations. Okay, so there are things that go into the Lagrangian. So when you have these particular constitutive relations, then your G-strand equations are in the realm of completely integrable PDEs with soliton solutions.
But usually a lax pair is not enough, right? Are there more indications in this direction showing that you do have a completely integrable?
Yeah, once you have this is called zero curvature representation. Once you have that, then you connect this problem to the Riemann-Hilbert problem. And the Riemann-Hilbert problem is also connected to isospectral problems and will give you, there's a matrix called the monodromy matrix, and the traces of the powers of the monodromy matrix will give you all the constants of motion you need, and they'll be functionally independent. And the problem will be completely integrable.
So these things are known and are...
Yeah. This is just like I said, it's making the connection to the theory of solitons. Okay, and once you get the zero commutator relation and you've solved these extra constraints that come into the problem, because L with M gives you a lambda to the fourth, gives you a lambda to the third, and a lambda squared, which is not in the linear terms. Okay, so you can make the lambda squared go away by having A and B be independent of time and space, just constants. Okay, but you still you will have a relationship at lambda squared, lambda cubed, and lambda to the fourth, and they will give you relationships that are constitutive relations. And when they hold, then the zero curvature relation is satisfied. That fits with Riemann-Hilbert, and off you go.
Maybe we can discuss it after that, because we
Any more?
keep people from lunch. And
Yeah, okay.
It's dangerous.
Yeah.
Discussion can continue.
What? Okay, so thank you.